Download this code from codegive.com, link in the description below. OK, let's dive deep into Niall Douglas's Racing the File System talk from Cppcon 2015. This was a truly eye-opening presentation on how to drastically improve file I/O performance in C++ by understanding and exploiting the underlying operating system and hardware. This tutorial will 1. Introduce the problem *, explain why traditional C++ file I/O is often slow. 2. Explain key concepts *, introduce concepts like memory mapping, direct I/O, asynchronous I/O, and Linux's splice. 3. Walk through the talk's content *, systematically cover the techniques and code examples Niall discussed. 4. Provide code snippets and explanations *, give C++ code snippets to illustrate the concepts, along with detailed explanations. 5. Discuss best practices and caveats *, highlight considerations for choosing the right approach and potential pitfalls. 6. Offer further resources *, point to relevant libraries and resources for continued learning. 1. The problem: why is file I/O slow? Traditional C++ file I/O, as taught in most introductory courses, often relies on functions like std_ifstream, std_offstream, fred, frit, and iostream. While convenient, these functions frequently involve multiple layers of buffering and data copying, which can significantly impact performance, especially when dealing with large files. Here's a breakdown of the common bottlenecks. System calls every time you use a function like fred, the program makes a system call to the operating system's kernel. System calls are relatively expensive because they involve a context switch from user mode to kernel mode. Kernel buffering the operating system typically employs its own buffers, the page cache or buffer cache, to cache recently accessed file data. This can improve performance for repeated reads of the same data, but it introduces an extra layer of copying. When you fred, the data is read from disk into the kernel's buffer, and then copied again into your program's buffer. User space buffering C++ I/O streams often add another layer of buffering in user space. This is done to optimize small reads and writes, but it can become a hindrance when dealing with large blocks of data. Context switching excessive context switching between user space and kernel space is very expensive. 2. Key concepts. Before we dive into the specific techniques, let's define some key concepts. Memory mapping. This is a technique that allows you to map a file, or a portion of a file, directly into your program's virtual memory space. The OS handles loading pages from the file into memory as needed, demand paging. This eliminates the need for explicit read or write system calls and potentially reduces copying. Direct I/O, O_direct. This flag, when used with Open on Linux, bypasses the kernel's page cache. Data is read directly from disk into your program's buffer, or written directly from your buffer to disk. It requires special considerations for buffer alignment. Asynchronous I/O, AIO. This allows you to initiate I/O operations without blocking the calling thread. The OS handles the actual I/O in the background, and you can later check for completion. This is crucial for achieving high throughput by overlapping I/O with other tasks. Splice, Linux. A Linux-specific system call that allows you to move data directly between file descriptors without copying data through user space. It's highly efficient for tasks like copying data from one file to another. 3. Niall Douglas's talk, Racing the File System. Niall's talk explores these concepts in the context of achieving maximum file I/O performance. Here's a breakdown of the topics covered. The problem he starts by highlighting the inefficiencies of traditional C++ I/O, as described above. he emphasizes the need to minimize system calls and data copying. Baseline performance. He establishes a baseline by measuring the performance of std ifstream, std offstream, fred, and frit when copying a large file. Map, memory mapping. He demonstrates how map can improve performance compared to the baseline by eliminating the need for explicit read and write calls. Direct IO, O_direct. He shows how O_direct can be even faster by bypassing the page cache, but he also discusses the limitations and caveats. Asynchronous IO, AIO. He introduces asynchronous IO to overlap IO operations with other processing, significantly increasing throughput. Splice, Linux. He demonstrates how Splice can achieve near-perfect performance for copying files, as it avoids all data copying through user space. 4. Code snippets and explanations. Let's illustrate these techniques with code snippets. Note that some of these techniques are platform-specific, example O_direct and Splice are Linux-specific. 4.1. Baseline, using fred. Explanation asterisk. This code copies a file using fred and frit. It reads data in chunks of buffer_size from the input file and writes it to the output file. It measures the time taken for the entire operation. This is a simple baseline implementation, and its performance is often limited by buffering and system calls. 4.2. Memory mapping, map. Explanation this code uses map to map the input and output files into memory. Open creates file descriptors, fstat gets file size. Map maps the files into memory. The flags prot_read allows reading, prot_write allows writing. Map_shared means changes are visible to other processes. Truncate makes sure the output file is the correct size. Mempb copies the data from the input memory region to the output memory region. Crucially, this is not a system call. MSYNC forces the changes made to the output memory region to be written to disk. This is very important, or the copy may be delayed and the timing may be inaccurate. Munmap unmaps the files from memory and closes the descriptors. 4.3. Direct IO, O_direct. Explanation O_direct flag the open calls now include the O_direct flag. Alignment buffers used with O_direct must be aligned to the file system's block size, typically 512 bytes or 4096 bytes. P6_mammalian is used to allocate aligned memory. Pred and prit these functions perform pred/prit without affecting the file offset. Error handling robust error handling is crucial with O_direct. Padding O_direct also requires that the write must be in multiples of block_size, so you might need to pad the last block. This is shown in the code above. Important considerations for O_direct alignment this is the most critical aspect. Failure to align buffers correctly will result in errors. The alignment must match the logical block size of the disk. Use the stat system call or fstat to get the relevant parameters. Buffer size reads and writes must be in multiples of the block size. Performance tuning O_direct can be very fast, but it requires careful tuning. The optimal block size depends on the hardware and the workload. Experimentation is often necessary. Data integrity since O_direct bypasses the page cache, it's important to ensure data integrity. Consider using checksums or other error detection mechanisms. Asterisk metadata asterisk using O_direct can bypass the file system metadata cache, so you can see increased metadata operations depending on what operations are being done on the file. 4.4 Asynchronous I/O, AIO. Explanation asterisk. Asterisk includes asterisk the code includes libio.h for asynchronous I/O functions. Asterisk IO underscore setup asterisk this function initializes an AIO context, which is a handle for managing asynchronous operations. Asterisk IO underscore prep underscore pred asterisk this function prepares an IOSIB, IO control block, for a read operation. The arguments specify the file descriptor, buffer, size, and offset. Asterisk IO underscore submit asterisk this function submits the IO request to the kernel. The request is non-blocking, the function returns immediately. Asterisk IO underscore get events asterisk this function waits for IO events to complete. It blocks until at least one event is available. Asterisk IO underscore destroy asterisk this function releases the AIO context. Asterisk overlap asterisk this code attempts to overlap read and write operations. It starts by submitting multiple read requests, and as each read completes, it immediately submits a corresponding write request. Asterisk event handling asterisk the IO underscore get events function returns information about the completed IO operations, including the result, number of bytes read or written, and any errors that occurred. Asterisk O underscore direct asterisk AIO typically works best in conjunction with O underscore direct to avoid double buffering. Asterisk request underscore index. The request underscore index is used to keep track of which buffer is being used in which IO underscore CB. Important considerations for AIO asterisk. Asterisk complexity asterisk AIO is significantly more complex than synchronous IO. The code is more difficult to write, debug, and maintain. Asterisk error handling asterisk robust error handling is crucial in AIO code. You need to handle errors that may occur during submission, completion, and cancellation of IO requests. Asterisk resource management asterisk AIO requires careful management of resources, such as AIO contexts, IO control blocks, IOCBs, and buffers. Asterisk kernel support asterisk AIO is not supported on all platforms. It is well supported on Linux, but support on other operating systems may be limited. Asterisk context switching asterisk while AIO avoids blocking the calling thread, it still involves context switches between user space and kernel space. Excessive context switching can negate the benefits of AIO. 4.5 Splice, Linux. Explanation asterisk. Asterisk pipe asterisk a pipe is created to act as an intermediary buffer. Asterisk splice asterisk the splice system call transfers data between file descriptors. In this case, data is spliced from the input file to the write end of the pipe, and then from the read end of the pipe to the output file. This avoids copying data through user space. Asterisk efficiency asterisk splice is extremely efficient for file copying, often achieving near hardware limits. Important considerations for splice asterisk. Asterisk Linux specific asterisk splice is a Linux specific system call. Asterisk file descriptors asterisk splice works with file descriptors, not C++ streams. Asterisk limited functionality asterisk splice is primarily intended for copying data. It doesn't support transformations or other operations on the data. 5. Best practices and caveats. Asterisk profile your code asterisk don't blindly apply these techniques without profiling your code first. Identify the file I/O bottlenecks and choose the appropriate solution. Asterisk consider your use case asterisk the best approach depends on your specific requirements. If you need to read the entire file into memory, map might be a good choice. If you need to copy a file, splice, on Linux, is often the fastest option. If you need asynchronous I/O, AIO is the way to go. Handle errors. File I/O can fail for various reasons. Always handle errors gracefully to prevent crashes and data corruption. Portability. Be aware that some of these techniques are platform specific. If portability is a concern, consider using cross-platform libraries or abstractions. Trade-offs. There are trade-offs associated with each technique. Map can consume a lot of virtual memory. O_direct requires careful buffer alignment. AIO adds complexity to the code. Cache flushing. Always use MSYNC after writing to a file using map to ensure data persistence. 6. Further resources. Boost.agio. A cross-platform C++ library for asynchronous I/O. It provides a higher-level abstraction over operating system-specific AIO interfaces. Poco libraries. Another cross-platform C++ library that includes support for file I/O and networking. Operating system documentation. Consult the documentation for your specific operating system to learn more about file I/O APIs and options. Niall Douglas's blog and GitHub. Check out Niall Douglas's blog and GitHub for more information and code examples related to file I/O performance. Cppcon presentations. Search for other Cppcon presentations related to file I/O and system programming. In conclusion, Niall Douglas's Racing the File System talk is a valuable resource for C++ developers who need to optimize file I/O performance. By understanding the underlying operating system and hardware, and by using techniques like memory mapping, direct I/O, asynchronous I/O, and splice, you can achieve significant performance improvements. Remember to profile your code, consider your use case, handle errors, and be aware of the trade-offs involved. The code examples provided here should serve as a starting point for your own experimentation and optimization efforts. Good luck.